Hello viewers, welcome back to my channel. Hope you are doing great. If you haven't subscribed to my channel yet, please go ahead and subscribe. I have created bunch of playlists to cover various categories of the problems such as trees, graphs, dynamic programming, breadth first search, linked list, depth first search, binary search and so on. Please don't forget them to check out. I have uploaded the code for this particular problem to GitHub repository. You can get the link from description below this video. Let's jump into today's problem. Count good nodes in binary tree. Given a binary tree root, a node x in the tree is named good if in the path from root to x there are no nodes with a value greater than x. So, return the number of nodes in the binary tree. So, number of good nodes in the binary tree basically. So, what is a good node? Basically, from root to that node's path, if there is no node which is greater than x, right, then it is called as a good node. So the path is from the root node to the current node. So if you are looking at the current node, right, so from the path to the root node to the current node, there should be any node value which is greater than the current node. In that case, we will say the current node is a good node, right? So let's go ahead and try to understand through the example, right? So example 1, 3. So that is a root node. Obviously there is no node before the root node, right? So we will say, okay, root node is always a good node, right? As long as root node is there, we will just say, okay, root node is always a good node, because there is no node prior to root which is greater than the root node value, right? So 3 is good node. That's why it is put into the blue color here, okay? And I'm going on to the left subtree first. So 1. So is 1 greater than 3? No. So the path from root node to 1 is 3, 1, right? So 1 is not value, not greater than 3, right? So we will say 1 is not a good node. And going further, so for 1 there is a left subtree 3. So is there any node more than 3 prior to the leaf node 3? No, right? Is there any node which is prior to 3 and also greater than 3? No. So there is 3, but the 3 is not greater than 3, right? They are equal. So even in that case also, we will say the leaf node 3 is also a good node. So the good node means if in the path from root to x there is no node with value greater than x. So until this, under the left subtree 3, 1, 3. So for the last 3 there is no node which is greater than 3, right? We will say 3 is a good node. So from left subtree, when we went through, right, there are 2 good nodes we found, the root node 3 and the leaf node 3. So let's go on to the right subtree of root node. So we went to the first, that is 4. We are at 4, right? Is there any node which is greater than 4 from root to leaf? No. Then we consider 4 also as a good node. So how many nodes so far? 3 nodes. And go to the left subtree now. So from root to the leaf 1, 3, 4, 1, right? So for 1, is there any node greater than 1? Of course. 4 is greater than 1 and 3 is greater than 1. So we won't consider 1 as the good node. So going on to the right subtree 5. Is there any node from 3 to 5? Is there any node which is greater than 5? No. Then we will say 5 is a good node. So on the whole, this tree, the example 1 tree, has 4 good nodes. Okay. So that is how we have to understand. So at any given point in time, we care about what is the maximum value that we have seen so far, right? In other words, so what is the maximum value that we have seen so far? If the current node is greater than the maximum, then we are good. All that if we check that thing, right, then we are good. We actually don't need to go through the entire path. So let's say for this example node, 3, 1, 3 is the path for left subtree, and 3, 4, 1 is a path for the leaf node 1. and 3, 4, 5 is the path from 3, 4, 5. That is completely the right subtree, right? Starting from root to leaf. So 3, 1, 3, if you look at it, right? So 3 is good because it is the first node. 1, so 1 is not greater than 3, right? So we will say 1 is not a good node, right? So 1 doesn't follow equal or increasing order. So basically the order that I am calling here is, so as long as it follows the equal or increasing to the previous maximum, right? If it is equal to the previous maximum, then we will still consider it is good node, or if it is more than the previous maximum, still we will consider it as good node, as long as it is not less than the previous maximum, right? So 1 is less than the previous maximum, that's why 1 is not following the equal or increasing order. So we will knock the 1 off, right? So 3, 4, 1, same here, 1 doesn't follow, 3, 4 and 1 is less than 4 and 1 is less than 3 also, right? So it doesn't follow equal or increasing order. But 3, 4, 5, the right subtree or rightmost subtree we can say, right? 3, 4, 5, they are all in increasing order. So 3 will be, 4 is greater than the so far maximum is 3 and 5 is so far maximum is 4 greater, right? So all are increasing order. So we will say all these 3 nodes follow it, right? In that particular say. So those are the root to leaf paths, right? So while doing that, we will come up with whether any node is following the equal or increasing order or not. If they are not following, then we will say they are not good nodes anymore, right? If they are following, yes, that is a good node. So that is what essentially we need to look for, right? So as long as we keep track of the current node and the maximum so far, right? If the current node is greater than or equal to the maximum so far, right, we will say the node is good node. So what is that? Current node, right? Current node value. So current node value is greater than or equal to maximum so far, right? Maximum so far. Then we will say good node. Otherwise, it's not. So that's a simple thing. In the previous example, right, I was going through the root to leaf paths, but do we really need to go through the root to leaf in order to identify that? Actually, we don't have to do that. At any given point in time, if you are able to identify this condition, what is the current node value and maximum so far that we have seen, if we know these two pieces of information, we are able to make a decision whether the current node is a good node or not, right? So all we need is these two pieces of information, right? So since we need these two pieces of information, I am going to have a placeholder class, right? I am going to have a placeholder class to keep track of these two. What is that? Current node and the maximum so far, right? I will have a placeholder class. Okay, let me go show the placeholder class. So this, I am calling it as a node. Node will have the tree node and maximum so far. So these are the two placeholders that I will have. So this is anyway constructor, I am initializing the tree node with the maximum value, right? So this is a placeholder class I will be using, right? So, and I will employ the BFS algorithm to solve this. So we will go through the breadth first search and go through each and every node in that particular binary tree and count as long as this condition is satisfied, right? As long as that condition is satisfied. We will keep track of the counter, and that condition is, once the condition is satisfied, we will increment the counter, right? So finally we will return the counter, whatever the counter that we have accumulated so far. So the algorithm we are going to use is BFS, and the condition is current node value is greater than or equal to maximum so far. So we will have to keep tracking the maximum so far, right? So let's go jump into the code and how we are going to look at the maximum so far tracking, right? So the code is, to start with, we will check whether the root node is null or not. If root node is null, there are no nodes, right? So we will just simply return 0, right? And we will initialize our counter. This counter will keep track of how many good nodes are there, right? So counter is initialized to 0. So since I said I will be doing this problem with breadth first search, BFS, right? So BFS is naturally uses the queue. So I am declaring a queue. My queue has the nodes, right? It doesn't have the tree node, but the node class, which is a placeholder class that I showed you earlier. So this is a placeholder class, right? So it will hold object of type node. Okay. So to start with, I will put the root node and root node value as the maximum, because to start with, that is the maximum that I have, right? So I will insert into the queue, enqueue that particular node with the root and root's value. So I will be going through this while loop while the queue is having at least one element, right? While the queue dot count is not equal to 0, I will be going through this particular algorithm. So get the node from the queue. So queue is a first in first out type of mechanism, right? So it will dequeue whatever the first in node, and now we will verify whether the node value is greater than or equal to the maximum so far. If so, we will increment the counter. That's what we said, right? So the condition is current node value is greater than or equal to max so far. If so, that is called as good node, and we will increment the counter. So that is what we are doing simply. So the current value is greater than max so far. We will just increment, right? And what we do next? So if the current nodes have left subtree or left child, we will do something. And if the current node has right child, we will do something. So what we are doing, essentially we are filling, or we are adding this left child to the queue and right child also to the queue, as long as the left child is existing and right child is also existing, right? So if the left child is existing, we will put the node's left child, right? Node's left child. And this is where we are keeping track of the maximum value, right? So what is the maximum so far? We need to update that. So we will put the maximum so far and the left node's value, right? And maximum so far and right node's value. So we are pushing into the queue, or we are enqueuing into the queue with the maximum value and the corresponding right node and corresponding maximum so far, right? So this while loop will be executed till the queue has at least one element, right? So once we exit this while loop, we will know the count of how many good nodes are there, as long as they are satisfying this condition. So we will return the count at the end, right? So this is how we are using the BFS, breadth first search algorithm, to solve this particular problem. So let's go ahead and look at the time complexity, right? So time and space, right? So time complexity. So let's say there are n nodes in the binary tree, right? So each node is being visited once, right? Each node is being visited once, and it is being put into queue and got out of the queue, right? So what does that mean? We are going through the complete tree once. So order of n, basically there are n nodes are there, so we will say order of n. So the time complexity for this particular algorithm is order of n, where n is the number of nodes in this given binary tree. And space, so how much space actually we need, right? So we are using this integer variable that will be constant irrespective of the number of nodes in the binary tree, because we are just using one counter, and the extra space that we are using is for the queue, right? But what is stored in the queue? Two pieces of information, right? Node, that is tree node, and int max so far, right? So these two pieces of information. So how many nodes, how many such nodes are being stored in a given queue, right? That will be at the max equal to the maximum number of nodes in the given level, right? So there is something called level in the binary tree, right? So the number of nodes in a given level are, so if the levels are starting from 0, right? Levels start from 0. So at a given level, there are 2 power level number of nodes. 2 power level number of nodes are there in a given binary tree, number of nodes, right? Number of nodes. So level L has 2 power level number, right? So for example, level 0 has 2 power 0 is 1. Level 1, 2 power 1, 2 nodes. Level 2, 2 power 2, 4 nodes. That is the maximum. So that is the maximum number of nodes possible, right? So what we are going to say is, for a given level, there are 2 power L nodes that are possible. So what we will say is, the queue will have at the max at a given time maximum of 2 power level number of nodes, right? So the space will be equal to the, what is the maximum level in the given binary tree? We don't know that, right? So let's say the space complexity will be equal to 2 power max level, right? So that much memory we need for the queue. But keep in mind, we are not storing that permanently or till the end of the algorithm executes. So the nodes are coming into the queue and going out of the queue. So this is the maximum that we need. So order of 2 power max level in the binary tree, right? So space complexity is order of 2 power max level in the binary tree, and time complexity is order of n. If you have any further questions, please post them in the comment section below this video. I have posted the code for this particular problem to the GitHub repository. You will find the 2 links, one for C# and another for Java. So 2 languages, the code is available. You can get the link in the description below this video. If you haven't subscribed to my channel, please go ahead and subscribe and share among your friends. Please click on the bell icon so that you will be notified about my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe. Goodbye.